They heated whole houses in the 1940s with no power, and honestly, it still beats most modern systems. The lights went out first. Then the radios went quiet. Elevators froze between floors. But in millions of homes across Europe and North America during World War II, the radiators stayed hot. Not just warm, hot. Entire buildings held livable temperatures through blackouts, fuel rationing, and even bomb damage. No electric pumps, no fans, no smart controls, just iron, water, steam, and physics doing exactly what physics does every single time. This wasn't luck. It was design. And once you understand how it worked, you'll realize how fragile modern heating really is. This matters to anyone who studies history seriously. And it matters even more if you care about resilience. Because the people of the 1940s didn't just survive winter. They engineered around failure. By the early 1940s, electricity was unreliable by design. Power stations were targets. Rolling blackouts were honestly pretty common. Fuel shipments were inconsistent. Coal was rationed. Oil was scarce. Cities expected infrastructure to fail and planned accordingly. A heating system that stopped working when the grid went down was worse than useless. It was dangerous. So engineers leaned into something older and far more reliable than motors and switches. They leaned into gravity, convection, and thermal mass. Heating systems were stripped of unnecessary complexity. Fewer moving parts meant fewer failure points. The goal wasn't comfort in ideal conditions. The goal was survival in the worst ones. Radiators weren't accessories. They were the backbone of a passive circulation system that assumed the power would go out and kept working anyway. The heart of the 1940s radiator trick was gravity circulation. Hot water is lighter than cold water. That single fact powered entire homes. A boiler, usually coal-fired or wood-fired, sat at the lowest point of the house. Basement level. When water inside the boiler heated up, it expanded and became less dense. That lighter hot water naturally rose through supply pipes toward radiators placed higher in the building. As the water released heat inside those radiators, it cooled, became denser, and sank back down through return pipes to the boiler. No pump pushed it. Nothing pulled it. The loop ran continuously as long as heat was produced. Here's the detail modern builders forget. Pipe size mattered more than pressure. These systems used thick, wide-diameter pipes, big iron lines with gentle slopes. That reduced friction and allowed slow but unstoppable circulation. It didn't rush. It didn't need to. It just moved. Hour after hour, day after day. As long as the fire burned, the house stayed warm. Power outage or not. You can't separate the heating system from the building itself. In the 1940s, houses were designed to work with heat, not trap it. Radiators were oversized by modern standards and placed with intent, under windows, along exterior walls, at stair landings. This wasn't decorative. Cold air spilling through drafty windows would fall directly onto the radiator, heat up immediately, and rise back into the room. That created a natural convection loop without a single fan. Stairwells weren't dead space. They were vertical heat chimneys. Warm air rose naturally, pulling heat upward and distributing it floor by floor. A boiler in the basement could heat an entire multi-story house because the house itself encouraged air movement. Instead of forcing air mechanically, these homes invited it to move naturally. Every layout choice mattered. Furniture placement mattered, door positions mattered, even ceiling height mattered. Lower ceilings meant less volume to heat and faster stabilization. This wasn't accidental efficiency, it was intentional design under pressure. One of the smartest wartime upgrades didn't burn a single extra ounce of fuel. Exterior walls, especially brick and stone, absorbed enormous amounts of heat and leaked it outdoors. People figured this out fast, so they started installing reflective shields behind radiators mounted on exterior walls. Polished metal, tin sheets, aluminum scraps, flattened ration tins, anything reflective. The idea was simple. Instead of letting radiant heat soak into the wall, bounce it back into the room. The temperature difference was immediate and noticeable. Rooms warmed faster and stayed warmer longer. Fuel consumption didn't change. Output did. This wasn't theoretical. Households saw real gains during winters when every pound of coal mattered. And the physics hasn't changed. Radiant reflection still works today just as well as it did then. Why steam systems were loud, ugly, and brutally effective. In dense urban areas, steam radiators often outperformed hot water systems. Steam rises faster than water flows. That gave these systems aggressive heat delivery with zero electrical assistance. A steam boiler converted water into steam, which rushed upward through pipes into radiators. Air inside the radiators escaped through small mechanical vents. Once filled with steam, the radiator released massive amounts of heat as the steam condensed back into water. That water then flowed back to the boiler by gravity. No pumps, no electronics, just pressure differentials and phase change doing the work. These systems banged, they hissed, they rattled, and they kept people alive during blackouts when electric heaters failed instantly. In apartment buildings especially, steam heat was a lifeline. One boiler could serve dozens of units even under unstable conditions. Precision mattered, vent timing mattered, pipe slope mattered. But once dialed in, steam heat was relentless. How people actually lived with these systems during wartime. Heating wasn't isolated room by room. It was managed as a whole-house ecosystem. Doors were often left open deliberately to allow heat to travel. Heavy curtains were used strategically, not everywhere, to block drafts without trapping heat. Thick rugs reduced heat loss through floors. Furniture was positioned to avoid blocking radiators or air paths. Thermal mass was embraced. Brick, stone and iron absorbed heat during peak firing and released it slowly overnight. This stabilized temperatures and reduced fuel demand. People understood that short bursts of intense heat were inefficient. What worked was slow, continuous warmth, steady fires, steady circulation, steady living conditions. This mindset alone separates wartime heating logic from modern habits. Why these systems vanished after the war? Cost and speed killed them. Electric pumps allowed thinner pipes and faster heat delivery. Compact boilers reduced material costs. Builders could throw up houses faster and cheaper. Convenience replaced resilience as the primary goal. But every pump added a dependency. Every control board added fragility. When the power fails today, most modern heating systems stop instantly. The old systems kept going because they didn't know the power was gone. That trade-off made sense when electricity was cheap and reliable. It makes less sense now. What this teaches us about real resilience. The lesson isn't nostalgia, it's systems thinking. The 1940s radiator approach assumed disruption as normal. It planned for scarcity, failure and damage. It respected physics instead of fighting it, and because of that it failed gracefully instead of catastrophically. For historians, this reveals how civilian engineering adapted under extreme pressure. For survivalists, it offers a proven blueprint that doesn't rely on fragile technology. How to apply this logic today in real life? You don't need to live in a 1940s townhouse to use this knowledge. An off-grid or preparedness-focused home can replicate these principles right now. A wood-fired boiler or masonry heater placed below radiator height can circulate hot water naturally if pipe diameters are large enough and slopes are correct. Pumps become optional instead of mandatory. Old cast-iron radiators can be salvaged and reused. Modern gravity-rated radiators exist as well. Reflective shields behind heat sources still provide measurable gains. Thermal mass placed near heat emitters improves stability. Inside the home, allow heat to move. Don't choke it with unnecessary barriers. Keep air paths clear. Use curtains and rugs deliberately, not indiscriminately. Think in terms of whole house flow, not isolated rooms. Most importantly, design systems that keep working when components fail. That's the real wartime lesson. History already solved many of the problems we're pretending are new. If this deep dive sharpened your understanding of how people actually lived, adapted and engineered under pressure during World War II, subscribe to Old World Prep. Share this with someone who still confuses modern convenience with resilience, and stay sharp, because the past has more answers left to give.